And we'll get started. So today we're going to continue where we left off with, we're looking at flight decks and instrumentation, and then we should make it into caution and warning kind of in the second half of lecture items today. But we left off here, we were looking at flight deck design philosophy, and we talked through these different items here, things being, logical, frequency used, tactile, standardized, and that kind of thing. The next part of flight deck design philosophy is another very important one is what's called the dark flight deck concept. And I talked with a couple groups yesterday when they were in the sim about this. Not everyone asked, but there was some question about that. But the dark flight deck concept is that the key point is we want to minimize distractions. And by minimizing distractions, we can draw attention to an abnormal or a non-normal situation when one occurs, and it doesn't get lost in a sea of other things going on. So what I mean by that is during normal cruise flight, right? So or with an ICAS or ECAM system that's dynamic, it'll be in the flight phase. The flight deck should be as dark as possible. So that means that on your ICAS displays, there shouldn't be any caution, warning, or other messages like that. Okay, it means that on your glare shield and your overhead, there shouldn't be any lights turned on. Okay, so when things are normal, the lights shut off. Your indication lights shut off, the messages go away, things are quiet, and things don't, there aren't any attention-grabbing kind of items. And so what that means, though, is that with everything dark and quiet and calm, when there is something that becomes abnormal and a message pops up or a light lights up or some kind of an alarm or alert sounds or a haptic item occurs, which is haptic is feel. Think of some of you are probably familiar with like stick shakers or pushers or other things like that that provide some feel. That grabs the attention of the person operating the aircraft, the crew member. Or on the ground, it could be you as a maintenance personnel. When we're running aircraft on the ground, we may not have every single thing. We don't have quite a dark flight deck. An example of that would be we probably have some kind of a landing gear down indication. Right? Normal in flight is the landing gear is retracted. So we'll have a down and locked indication for the landing gear. That won't go away on the ground. Okay, that disappears in flight once the gear is brought up. We may not have our engines up at a flight level, and so something like oil pressure may not, may be in a yellow range rather than a green range on a gauge. Okay, green also is normal for the things that do show up. Typically, green is normal, yellow is cautionary, and red is warning. Okay, sometimes you also hear them referred to as amber and red, right? Instead of yellow, it'll be amber as caution. So we want the attention of the operator to be grabbed when necessary. So here I've got just a real short, kind of a YouTube short of a Bombardier Vision where they go through the Vision flight deck system, which is a modern flight deck designed with dark flight deck concept in. So we got that attention grabbing. Another thing we have is our indication. What drives those indications? When we don't have a dark flight deck, what causes that indication? And so we have something called a loop of control or an input control feedback loop. And that is the input is not typically what drives the indication. And what I mean by that is that here I have an example of I push a switch or flip a switch to turn on a fuel pump, right? And then there's usually like a fuel pressure warning light or fuel pressure caution light. That light is not shut off by the action of moving the switch. The action of moving the switch sends power to the pump. Downstream pump, there's a pressure switch or a pressure sensor. And when that actually senses fuel pressure, it then turns that light off up in the flight deck. So while you're in flight, say that pump fails, the switch is on, but the pump fails, there's a loss of pressure, then that light comes on to tell you that the pressure has gone away, okay? The same thing with hydraulic systems. You turn the hydraulic pump, electric hydraulic pump switch on. That causes, so that's your input. That control or movement is that pump activating. And then it builds pressure in the system downstream, and there's a pressure switch that then feeds back to the low pressure light to shut it off. Okay, yeah. It works the same way with engine oil pressure. Well, engine oil pressure is a pressure you would start the engine would be running, oil pressure builds, your engine low pressure turns off, right? It works the same way even with flight controls. When we get to like flight controls on the ICAS indication, most ICAS systems have a flight control position indicator. You can look at where every flight control is on the aircraft relative to its neutral position. And the way that works is whether it is a mechanical flight control or a hydraulically driven flight control, a cable to hydraulic flight control, or a fly-by-wire electrical control system, is you provide an input on the yoke or the rudder pedals or the flap handle or the spoiler handle. And then you have movement of that control surface, and connected to that control surface is some kind of a sensor. Typically they're called a resolver or a VDT, variable differential transformer. That sends a signal back to the ICAS system that then moves the indication on the display to whatever position it's in. So it's not just an on or off, but it actually gives you a positional location, okay, a degree of deflection, up or down or left or right. Okay, so we'll see this input control feedback loop. You know, we're seeing it from an indication standpoint, but you will see it on every system in some way or another on the aircraft. It's the same type of system that happens. You experience this with your house with like your thermostat. You set a temperature, right? The temperature in your house drops. That's an input. Your furnace kicks on. Furnace starts to come up. The feedback is there's a temp sensor. When it senses that, you know, you're back to normal temperature, it shuts the furnace off, right? Or it reads out what that temperature is on your little display. So you see them all over the place, and they're in every system on the aircraft, and it's important to kind of understand that's what's happening, that it's not just you flip the switch to turn the pump on, that's also what shuts the light off. It's that feedback. Okay. So these feed in, we then have, we talked about our different generations of flight decks, and so what you're going to see now, pretty much any modern flight deck has what's called an EFIS system, or electronic flight information system. And this is not system information. That's the first thing I'm going to tell you. This really is not a system thing. This is more of an avionics navigation type setup, right? And this is the displays that replace your traditional instruments, that six-pack: airspeed, altitude, turn coordinator, heading. Who's the pilot? I'm trying to remember the six-pack. Airspeed, altitude, turn coordinator, heading. What am I missing? That's heading. What are the other two in the six-pack? I'll have to look it up. That's embarrassing. No, that's an engine instrument. Well, so yeah, so it's your flight instance. Oh, rate of climb, rate of change. I don't think so. Airspeed. Did I say airspeed or did I miss airspeed? Yeah. Compass. There's 5. Yeah, turn coordinator. Yeah, there you go. So this is going to replace those six-pack, what's called the six-pack, with typically most aircraft have 2 displays: a primary flight display and a multifunction display. And usually on most of these aircraft, the primary flight display artificial horizon. There's the one I was looking for. So that's your attitude, right? Indication. So on your primary flight display, that one usually has airspeed. It usually has altitude. It usually has that artificial horizon that shows your attitude, right? Sometimes it has a turn coordinator, that kind of thing. The multifunction display often is used for the navigation instruments. That shows your heading. That shows your VOR, your localizer, those kind of things. So that's the normal display you'd have on those. On transport aircraft, the multifunction display often also has your weather radar. You can flip it over to see your weather radar. You can change it to go to TCAS, terminal collision avoidance. That's looking at where other aircraft are, right? So that's the primary multifunction display. Now, some aircraft are going to have ICAS or ECAM, engine indicating crew alerting system, or electronic condition and monitoring, depending on if you're in a Boeing, Embraer, Bombardier / Mitsubishi, they have ICAS, and Airbus decided to be different and call it ECAM, but it's basically the same thing. But do not say that to an Airbus engineer. I got a 20-minute lecture on how they're different. At the end, people don't know what the difference is. So at the end of the day, they basically do the same thing, but not all EFIS aircraft have ICAS. So there was a generation kind of in between where we had electronic flight displays, but we still had, for ECAS, for engine and system information, we still had your typical analog gauges. Okay, I've got some flight deck slides that I'll show in a little bit that kind of I can show pictures of it. So that's these flight deck iterations. So at first we had all gauges, right? Everything was those analog gauges, the 6-pack gauges instead of EFIS, the engine gauges, any of your system gauges, whether they were overhead on a smaller aircraft or back on the flight engineer panel on a larger aircraft. Then we went to the flight instruments, had the digital displays, primary multifunction display, but then your systems and engines were still analog. And then slowly those all became digitized, and now pretty much everything we have today, even down to something like our Cirrus, right? The small aircraft have pretty much all digital displays in them. So they have flight and engine and system information all on electronic displays. Okay, so EFIS is these two right here. Okay, flight instruments and then flight and engine instruments. ICAS is this bottom one. EFIS with ICAS is this bottom one here. Okay. So here is an example of pre-EFIS. Okay, this is the 727. Here's that 6-pack of gauges we talked about. Okay, they have a couple more, bigger airplane, right? But everything here is analog. These are your backup instruments are analog. Your engine instruments are analog. Over here on the right side, fuel. You know, there might be a few digital gauges. These were like the tank quantity gauges. They originally were analog, but then they put a little digital gauge that did the exact same thing. Just, you could see numbers so you could get a little bit more accurate reading rather than trying to read a scale. But, you know, electrical, everything there is analog. Down here, hydraulic pressures are analog. If we could look further over, we could see things like pneumatic pressures are analog and other stuff like that. So here is an example of that combo. So that first one was the gauges. This picture here is the second one, flight instruments only. Okay, so here you can see the primary and secondary flight display behind each pilot's yoke. Now notice what else they have next to those primary and secondary displays. What does it still have? It still has the 6-pack. It still has airspeed, altitude, heading, compass, navigation, you know. So they still had those. Those are kind of the backup gauges, but then you got backup in the middle. But the pilots in this case would use these EFIS displays 99.9% of the time. Okay. But we still have analog engine instruments here in the middle, right? And if I don't have an overhead view, but if you look at the overhead panel, this is a small plane, 34-passenger turboprop. Everything on the overhead panel is analog gauges. Analog gauge for hydraulic pressure, analog gauge for fuel, analog gauge for pneumatic pressure, right? So this is, flight instruments are digital. This has an EFIS primary and secondary flight display, but then it's got digital everything else. This little digital display in the middle is a weather radar. So a digital weather radar. Actually, if we go back to the 727, here's the weather radar down here in the middle. So weather radar was like the first thing to go digital. And then this also has, these are flight management systems, the computers for programming navigation on each side. This doesn't have an FMS. Actually, it's kind of built in. It does have one, but it's built into the primary and secondary flight display, the EFIS system. And then you get to that third generation. So here we have our flight and engine instruments. So flight displays, there's a pair of displays in front of each pilot. And then we have a pair of ICAS displays in the middle on the top there. And those two ICAS displays are going to have all your system. You're going to have engine instruments on the left one. You're going to have caution and warning messages, landing gear position. And then on the right one, you're going to be able to switch between all your different system information. There's a little control panel on this airplane. It's down here in the middle. Primary, electrical, hydraulic, and so on, to be able to switch what's on this display over here. Okay. So that's the third generation. Here's another third generation. Okay, we're in the third generation still. It's just the displays are getting bigger and there's more information on them. Okay. So Embraer 170, something like that. You can see here, here's your primary and secondary flight displays on both sides. You can see this one's got navigation on it on the secondary flight display. Primary, there's your artificial horizon, altitude, airspeed, heading, right? And then you've got a navigation on the secondary display. Over here, you've got your primary display. You can see still shows all your main flight instruments. And then on the secondary display, they've got an airport diagram. All right, so there you got airport diagrams, or you could pull up the weather radar, or you could pull up TCAS to look at where other aircraft are. And then in the middle here, we've got engine gauges, an area for messages, flap positions, landing gear positions, trims, and then the ability to pull up your secondary systems pages as well. Okay, and then these are your flight computers down here, or navigation program computers. Okay. It's an Embraer Legacy. That's a business jet. Sorry, I think I call it 190, 170, 190, and then the Legacy series are all interchangeable. I mean, the Legacy is the business jet version of the 170 family. Boeing 787, I believe. Boeing yoke, big displays. Yeah, it's not the 737 MAX. I believe this is the 787. Okay, you can see bigger displays. They've got, because the displays are so big now, right? This right here, these were cathode ray tube. These were flat screen, smaller flat screens, bigger flat screens. Okay, yeah, these cathode ray tubes. If you pull one of those things out, they're about that long. It comes out and it comes out and it comes out and comes out, and they weigh about 40 pounds a piece. The whole computer that runs it is behind it. Yep, they're big. Well, I mean, that much of it is the display tube in the front, and then you have an entire computer behind it. So this right here, these displays, about that thick, and that's the display and the computer behind it. Right, they're not that big. But they're much wider, much larger. So you have primary flight displays. You can have navigation information here. They kind of split them. Here's your primary ICAS display. Here's systems. Here's the co-pilot secondary display, co-pilot's primary display. You've got yet another, a whole nother like systems page down here. So you can put information here and here. Actually down here, you can put checklists on the lower display. So now their checklists are built right into the plane instead of having to pull out a book every time you wanted to go through a checklist. Right? Yep, that just technology enabled it. Okay. If we look up top, it's basically just buttons and dials now. There's no gauges or anything up top, and some warning lights. So ICAS, I said, was that engine indicating crew alerting. So that's those engine instruments and indication. Our messages, which can be classified into warnings, or red, cautions, or yellow, or amber. And then typically you have some kind of like status or advisory messages that are white and green, depending on the manufacturer. Some use more or less different colors and different names. System and aircraft information is available on, we call them synoptic pages. So you've all done some ICAS stuff on the 747 in lab, and you were hitting the buttons to go to the hydraulic page and the electrical page. Those are your synoptic pages, your system synoptic pages. Give you all your system information. But ICAS does not include those flight instruments. It does not include the primary and secondary flight displays. It's just those middle displays typically, whether they're side by side or whether they're above and below. Usually there's two. So ICAS, again, I mentioned is Boeing, Embraer, Canadair, Mitsubishi, most corporate jet manufacturers. And then ECAM is Airbus's special name for the same thing, but don't tell an engineer that. And it's just a different name acronym. But it is, so electronic condition, or so electronic condition and monitoring, or electronic centralized aircraft monitor. You'll hear it both ways. So it's a little confusing there when you see that two different ways, but. So again, here are those ICAS ECAM displays. Don't remember what aircraft. I want to say it's the 170 or the Legacy again. Something with Pratt & Whitney, or either got Pratt engines on it or it's got Rolls-Royce engines on it. Doesn't have GEs because it's got an EPR gauge at the top. So GE uses N1 for its primary power setting, and they don't show EPR typically. Here's another example. 4-engine aircraft. I think this was the BAE 145, the 4-engine high wing. I worked with some people that worked on them. They joked it was 4 APUs and a sewing machine. 146, yeah, BAE 146. They had 4 little tiny turbine engines, and then the APU was tiny, tiny. Yeah, they were very small, but it's a European. They work really well in mountain environments. Okay. Another thing that enabled this is we had older aircraft use something called discrete wiring, and that is you have one system or sensor or input driving typically one indication. You have a pressure switch, that pressure switch goes to a light. You have a pressure transducer, that transducer goes to a gauge, right? And it was typically only available by whatever it was wired to. So if we draw, inputs, we have an input, we'll call these, they can be inputs. We'll call this output. Sometimes an output can also be an input, but. So this was wired to this. This was wired to this. This was wired to this, right? Okay. If output number 3 wanted to see input number 1, 1, 2, 3, it didn't have a way to, we would have to like run another wire. You could have 2 wires coming off sometimes, right? Maybe you need to have pitot and static going to gauge 3, right? And gauge 1 maybe is just static for altitude, right? Altimeter, airspeed, right? Something like that. So it's not just wiring, it can also be, if you're doing electronic, it can also be piping as well. Okay, those outputs could be sensors that go to a light or something like that too. It's simplified. So these newer aircraft, one of the things we need to do is there's a lot of information. We want it to go to a lot of different places, and we want to be able to display it somewhere, right? And we want to be able to put it on multiple displays, right? Oftentimes we can move these displays around. As I mentioned on this one, and most of these, each of those displays has a computer on the back of it. We want that information to go to a lot of places, right? So most of these now have gone to, in order to enable that, we've gone to what's called a bus architecture. And that is, rather than doing discrete wiring, we put something in the middle called a bus. And all the data is on the bus. And then anything that needs the data off the bus can get data for a bus. And the nice part too is these can become 2-way streets. Say not only is this an output, but then it's got a button on it, right? It's a light that's also a push button, right? That push button could send data back to the bus, and that data may then go to gauge number 2, output number 2 or something, right? So we go to a bus architecture where everything, on the bus is available to everything else. Not everything's going to use every bit of data that's on there, but it's available if we want to pull it in somewhere. So it makes reconfiguration more possible. It allows us to have data in more places. Some of these could be the in-flight entertainment system. If you've flown on a modern aircraft with a sophisticated in-flight entertainment, They show the little map, and it tells you what your altitude is, what the airspeed is. It shows you the little plane overlay on the map of the Earth, right? That probably is pulling information from the same bus that the ICAS system is getting information, or the nav system's getting information from, or the EFIS system's getting information from. And you may have more than one of these at a time. I've got two of them. I've got ARINC 429 and 629 listed here. There are others as well. There are newer versions. Boeing, I can't remember, they developed a new one for the 787 that's even faster than these, and I don't remember what the number is for it. Most of them are referred to by a number. But so ARINC 429 was kind of was the first, and it still is probably the most common by far, because none of this stuff we're not sending high def television over this. We're sending like discrete numbers, right? What's the current altitude? 30,000 feet. That doesn't take a lot of data. It's not going to take long to transmit. So there's not a ton that needs super, super high speed buses. But we have exceeded the original speeds, so newer buses have come out. So ARINC 429 is the most common, and one aircraft may have more than one bus on it too, by the way. It may have some stuff that's connected by 429, something else, another group of things that needs high speed data is connected by a 629 bus. But it's more expensive, so, put the 429 where you need the slower speeds, 12.5 kilobytes per second or 100 kilobytes per second. That's pretty slow. Most of the things you're connecting with nowadays are gigabytes per second. So if you're not familiar, 1 megabyte is 1,000 kilobytes. 1 gigabyte is 1,000 megabytes. 1 terabyte is 1,000 gigabytes. If you have ideas of like your internet speed and stuff like that. All right, these can't transmit nearly as fast as your home network, but these are hardened, secure. They're networks that their reliability levels are far and away higher than what your home network is going to be if you do anything with networking. These have extra check. There's checks in them. They're designed for error prevention, those kind of things, right? We don't want erroneous data being fed into really important things like altimeters or stall indication or angle of attack, things that cause the plane to crash if it's wrong. Okay. So 429 came out in the 70s. ARINC 629 was developed in the 90s. That can run 100 megabits per second. The new Boeing one is in the gigabit range, couple thousand megabits per second. These are bits per second, not bytes per second. A byte is 8 bits, right? So divide them by 8 if you want to know if they're bytes per second. So the bus has multiple users, and these can be pretty much anything on the aircraft. I list a few things, but computers are the most common, but also other systems and instruments, your displays, different inputs like buttons and switches, right? Not everything is bus architecture, though. We still have a lot of discrete wiring in the aircraft as well. Don't get me wrong, it hasn't replaced everything, but a lot of the stuff that you see on your displays is going to be run through a bus. Okay. So with direct view wiring, when we had everything in there, that's where we saw more raw view. Pressure transducer puts a pressure on the gauge, right? The flight engineer has to look at that gauge, see what the pressure is, and then if that's correct, right? So flight crew monitoring, think of what you see. Well, 727 doesn't exist anymore. I can't show you that, but we can go look at the 747 panel. I just can't fire it up. ICAS, ECAM, a lot of that's interpreted view, right? A low pressure warning message on a hydraulic system is an interpreted view in there. Because you have a pressure transducer, it's sending a pressure to ICAS, and ICAS is saying if it's below this number, the warning message goes away. If it's below this number, the warning message lights up. If it's above this number, the warning message shuts off. Right? That's it's taking those numbers, those data, and it's interpreting it, and then putting the proper messages up, the proper indications up. Is it turning, something turning red, or something turning yellow, or something turning green on the display? Right? That's all interpretation of different data that's being fed in, rather than a gauge that just reads the hydraulic pressure is 3,000 psi, right? With a pointer pointing at 3,000, or if it's low, it's pointing at 0, or if it's in the middle, it's pointing at 1,500, right? So you did have some of that with, typically you'd have like a low pressure light or things like that as well. But again, those were raw. That was usually a pressure switch feeding a light rather than taking a pressure transducer and deciding, is this low or high? Right? That was done by a human when you had a flight engineer. So pilot, co-pilot displays are going to give you things like those messages. You're going to have the synoptic displays. And the really cool thing is they have dynamic information, and that is the information can change based on the condition of the aircraft, especially those really new ones. You know, going back to this right here, we have a checklist right here. It actually has the ability, if there's a warning, a serious thing that pops up here during flight, or even a yellow, a cautionary, a hydraulic low pressure, that can trigger the low pressure. You know, if you have low pressure in hydraulic system 1, what steps do you have to take to make sure things are safe? And the checklist, the non-normal, it's called the non-normal checklist, will pop up. And the pilot says, okay, check that the pump is on. Yep, I did that. You know, check that the circuit breaker is not. Yep, I did that. Oh, circuit breaker's pop. So that's like, okay, something in the pump caused an overcurrent. We're going to leave that off. Now what do we have to do to make sure that the plane's still safe to fly? And there might be other steps. Make sure system 2 and system 3 have pressure. Hopefully they do, right? If you lose a bunch of them at once, you're kind of in a bad spot. So that's, you get dynamic information. And then it can also change based on phase of flight. You know, newer aircraft, they know when they're on approach. The nav system tells them they're on approach. Okay. If the gear goes down in cruise, it's a much different scenario than if the gear comes down just before you land, right? And change how it reacts. Anything older, you're going to get the same indication no matter what. Gear down, gear up. But, you know, a gear down in cruise at 400 knots, that's like warning territory. A gear down on approach at 200 knots, that's normal. We'll probably do a yellow to tell you it's done, but you know, it's not like a warning, right? It's not going to rip the gear off. So, you know, this was your discrete wiring. We talked about ICAS and ECAM, had the bus architecture. There's, you know, different synoptic pages, just the different, you've seen the 747 ones. This is the Embraer ones. So you have a status page, kind of general information in a lot of areas. Here's a flight control one. That's the one I was talking about. It shows you positions of your different flight controls. Shows you the status. This one's hashed out yellow. It tells you something's wrong with that one. Either can't get a reading for it, it's not working. Hydraulics, including pressures, quantities, what systems they're operating. So if you lose a hydraulic system, it tells you what is not going to work, right? Fuel, electrical AC and DC, environmental control, which has pneumatics, where the different settings are, anti-ice, you know, and then a maintenance page. Now we had maintenance pages where these can be used in troubleshooting, that kind of thing. The maintenance page typically is not available in flight. That's something you have to have like weight on wheels to get to. Okay. They don't want pilots looking at maintenance pages in flight. They're not supposed to really troubleshoot in flight. They go through a checklist. They do what the checklist says. We don't want them doing more than that. Anyone know why? That was oxygen generators. But Puget Sound in Washington, there was a, who was it? What flight was it? It was a DC-9 or MD-80, something like that. They had a stab trim issue, the horizontal stabilizer, which is your pitch trim. It seized up. It's a big screw and nut. It's a jack screw. It seized up, and it kept popping the circuit breaker because of a high current situation. They go to move it, and they were in a normal, pretty normal range, flyable aircraft, right? So you could have flown it, you know, yeah, maybe you would have had to kind of fight the controls a little bit, but you could have flown the plane fine. They'd go to adjust it, it popped the circuit breaker. The crew turned around, pushed the circuit breaker in, tried to adjust it again. It popped the circuit breaker again. They kept doing that. They did that over and over and over again. What's that? They didn't fry it. They stripped the threads on that giant nut, or on that, actually it was on the screw, the big shaft that adjusts it. Now, the thing that holds the horizontal stabilizer in a certain position, holding it anymore, it was able to just flop up and down. They lost the ability to control pitch of the aircraft. And it crashed in, it was up in Washington it's the big bay of, was it Puget Sound or? Yeah, I think it was Puget Sound up there. If they just left it alone, they could have flown it. right? But they were trying to troubleshoot. So pilots are not supposed to really troubleshoot. There might be a little bit they can do, but not a lot. And so that's where that stuff gets locked out in flight. And you got to remember that too when you're working like a hangar. If you have a plane up on jacks, you won't be able to access those maintenance pages. Okay? So that's where it kind of applies to us. Okay? So that finishes that section up.